Okay, okay,
Thank
great.
you.
So the topics I would be addressing in this presentation is sequence to sequence model, attention mechanism, and the main focus is understanding transformer network, which was introduced in 2017 in this paper called Attention is All You Need. I'll also discuss in detail the transformer network. A couple of things that I have not included in this deck yet is the code for training the transformer model, and how do we evaluate that. So that two part is still I, I'm yet to add in this deck, but I'll discuss the entire process in detail. So when we talk about sequence to sequence model, I'll give you a quick introduction because the network we will be discussing is uh, primarily built for machine translation. So we will concentrate on like we will be our focus will be on machine translation problem. So sequence to sequence model, what it does, it takes a sequence of items. It could be words, letters, uh, and it outputs another sequence. So the model is composed of an encoder and a decoder. Uh, Ideally, like before the transformation became the state of art, RNN was used widely. So both encoder and decoder generally had a recurrent neural network within itself. Uh, so in the paper, in the transformer network, we will see that the entire focus on this network was based on attention mechanism. I will discuss attention mechanism in detail and how they are using it in the model. Uh, Here is just a context on why, with respect to the classic solution, if we call it a classic solution, RNN solution, how attention mechanism is different. So the the context vector in case of RNN makes it really challenging if it is a very long sequence. But like, I mean, if I won't go in detail how RNN works, but we know that it starts with one word and it goes sequentially. So when you have a large sequence of sentence or a large sequence, then it is very difficult to keep the context of the initial word intact. So in that case, attention model allows to focus on the relevant part of the input sequence. Again, I'll discuss the mechanism in detail in later slides. Um, so yeah, this is just an visualization to get what it is happening here in RNN solution. One input goes into encoder, comes out, and then for every uh, word, you will have the input word and the hidden state of the previous layer, right? But in attention mechanism, the decoder is presented with all the hidden states. It's not just presented with the last hidden state. So yeah, this is like explain a little more detail in how attention decoder looks. So it looks at the set of all the hidden states of the encoder, and thus gives a well-informed result out of it. Let's go deep into the transformer network. Why the transformer network was I mean, what is the motivation of this network? So, as I was saying, that this recurrent neural network, it's inherently sequential. So, which the problem is, you cannot do, like, there is a very minimal scope of parallelization normalization computation, right? Like you need hidden state of the last layer for the as an input for the next layer. So it's inherently sequential. So to and obviously it is computationally expensive as well, right? So to reduce this problem with this sequential network, we wanted to introduce parallelization in the computation. So these are the issues of the recurrent neural network. We will what and that is why in the transformer network you will see there's like no recurrent neural network was used. It was solely based on attention mechanism. Okay, so before going into detail, I'll just give an overview of what transformer network actually looks like. So, as I said earlier, it's based on attention model mechanism without any recurrence or convolutions involved. So if you look at the top level of the network, again, I'll discuss each layer, each step in detail going forward. But if you just see the overview, so it is again encoder decoder architecture. Both encoder has a fixed number of layers. So this is solely based on the paper. They have used fixed number of layers like 6 encoder layer and decoder layer, but this is not a magic number and not written in stone. Can be changed, but this provided a good results for them. The number 6. And if we look at the encoder layer, so each encoder layer has have two sub layers, one self attention layer and one pointwise feed forward layer. And the decoder has also the same two layers, but it has one additional attention layer that is called encoder decoder attention layer. So I'll discuss every steps in detail now. So this picture is from the paper itself. So this is the architecture, overall architecture. So here in this section is the encoder layer, and in this is the section for the decoder layer, and finally the output comes up. So I'll discuss one by one. So here, since the model was built for machine translation, so the example I'll be referring to is also like a translation problem. Say it can be English to French translation or French to English translation, whatever. So your data is a sequence of words, right? So your input is sequence of words. So when we talk about like modeling words, so it is important we convert each word into a vector representation, because your model won't understand text word, right? So every word is converted to a vector representation of that word. So there are a couple of algorithms that do this kind of work, like word to vec, subword embedding. I'll also explain these algorithm in here. So in trans in the paper, they have used this algorithm to convert every word to vectors. So this is a word to vec algorithm. So the word embedding is basically uh, representation of any word into a vector. So this can be simply done by one hot encoding, like if you see in this example here. So suppose, for example, we have this sequence of words. So we can definitely represent this as like 1000010. And you see, since we already have the twice, so we can use the same vector. this could be done, but there's some challenges with this technique, right? So we can like see and say that if this this is very small sequence, but our dictionary or the vocabulary that we will be using for training purpose, it's like huge, like 50,000 words or millions of words. So it will be a very big sparse matrix. So that is not desirable. Also, if you want to find any similarity between words, you won't be able to find with this vectors, right? So if you calculate any similarity, if you like dot product or anything, it will be always zero. So to overcome this, one of the algorithm that's used is what to vec algorithm. So um, in nutshell, you start with a large text data set. So each word in the fixed vocabulary is represented by a vector. We can start with start with any random vector, and then we'll optimize it based on some conditions. So we go through each word, and like in a text, we go through each word. So which is like there's two concepts. One is central target word, and another is context word. So when you're considering, for example, you're going through each of the text, and you're at this text, like as this word sat is your central target word, and the word the cat on the is your context word. Now, why I am taking two words only, it is also not like you can decide the window. It's a window of word you can decide uh, to think of as a context word. So we can use the similarity of word vector for context and central word to calculate the probability. Like I'll discuss it in the next slide what the calculation is, but we can keep adjusting the word to maximize this probability. So the probability of this word given I have the central word as sat. So we move on to the like once we decide on that, then we move on to the next word. So the word to vec model can use like there are two kinds of models. Like one is skipgram model, one is continuous bag of words. So the skipgram model assumes that word can be generated from a central word that surrounds it in the text sequence. And the continuous bag of words assumes that central target word is generated based on the context word. So in this presentation, I'm only explaining the skipgram model. You can look continuous bag of words as well, but you can use either of this. So in skipgram model, uh, this is how it is done. Like every word initially was represented by 2D-dimensional vector. One vector is central target word, and another is the context word. So for each word, we start with two vectors, random vectors. So once we have this vector, if you compare this formula that I've written here versus the one here, I have changed the notation as probability of vector u given vector v, because v is the representation of central word, whereas u is the representation of context word. So the this conditional probability of generating the context word for a given central word can be obtained by performing a softmax operation on the similarity calculation. Generally we take dot products of the vectors, and we can use a softmax function to get the probability distribution here. So as I was saying, I don't know, you can see this. Okay. This window size here, that is 2 in this example, can vary. Like when the context window size is m, then we can now calculate, we have the probabilities, so we can calculate the likelihood function, uh, the joint probability of all the context word given any central target word. So this will be our likelihood function. And yeah, and we're going to learn the parameters by maximizing this likelihood function, which is also equivalent to minimizing this negative log likelihood function, right? So we can use stochastic gradient descent to do this optimization. But we need to keep in mind that since we started with 2 vectors initially for each word, we will be like, finally when we optimize the result, we will also get 2 vectors for each word. So in application of NLP, ideally the central target word vector in this model is used. So there's another improved version of this algorithm known as Subword tokenization. Um, so this actually uses the same model, but it takes into account the principle of morphology. So what happens, for example, there are a few like uh, there are words which you may not find in the vocabulary you're using for training, but which could be used, like, merging 2 words together. Like it's in a regular uh, language. It's not only in English, but you will see in many other language that people tend to combine words and talk. Like, for example, a word like workaholic, it you may not find it in the dictionary, but uh, you have the subwords in the dictionary. Another example, like for example, dog and dogs, or like the association between dog and dogs, like similar association between other words like cat and cats. In the word to vec algorithm, this relationship is not represented to the models. So fast text proposes a subword embedding method, which is quite simple. I'll let me explain it first. Then, uh, yeah. So in this algorithm, what it is done is we first start with a special character, these 2 characters at the beginning and the end, beginning and the end of the word, and we create multiple subwords. Like ideally, it varies from 3 to 6, but it can be changed. So you create multiple subwords from your existing words. So your length of your vocabulary increases, and you have a bigger set of dictionary, and you then apply the skip drum model to it. So again, this is uh, an improved version in the sense this can address few of the complicated words that the model has not seen during training. But again, the disadvantages is computationally very expensive. But we do have a pre-trained model that we can use, like it's already there, and it's efficient. So yeah, I already discussed this, like what are the how it is different. The subword tokenization uses the morphology information, which the simple word to vec does not. um, and again, as I said, words like cat and cats will have 2 different vectors in word to vec, and their relationship, the association, is not directly represented in the model. Uh, so this is the initial step in the transformer network. So you have the inputs and you pass through an input embedding, like could be word to vec or subword tokenization. and you have vector representation of the word. You have to do this for each word in the sequence. The next step, if you see, it's the positional encoding of the vector. So since we have uh, s- like seen earlier, or we've discussed that no RNN or convolution is involved in this mechanism. So there's no information of the order of the sequence. I mean, in any translation problem, order of a sequence is important, right? If you change the order, the meaning can change drastically, right? So it is important. And here in this step, we will add positional encoding to account for this order. So to address this, the transformer network, what does it do? It adds a vector to each input embedding. So from the input embedding, you get a vector representation of your word, but which doesn't have any positional information to it. You add a vector to it. So in the paper, this formula is used. Uh, I mean, there's an intuition behind using this formula. So if you think about position, like incorporating positional information to a vector, you can use like actual position also, right? Like, say, for example, you have three words here. So this is your first word, this is your second word, this is your third word, and these are your input embedding vectors. So you can add, like, say, 0, 0, 0 for the first vector, the second vector 1, 1, 1, 1. So you can keep adding the position this way. But again, the problem with this, if you have a huge sequence, say you have a sequence of 30 words, so the like the final operation, final value from this will be like huge. It will explode with a as you go along the sequence, right? So that you cannot do. Now you can also try like using proportion as the positional vectors. So for example, if you have say four words, so you can just use the first vector as, say, 0, 0, 0, next one is 0.33, next one 0.66, then another one, the last one is 1. But if you do that, the problem is, like, this length of sequence of a sentence will not remain same for each sequence, right? So you have different length of sequences. So for the second position, for one sequence you will get 0.33. For any other sequence of larger length, you will get much a different number, right? But that is like, that is not desirable again. So that's why this is also, this could be learned through the model. So in the paper they have tried both, like they have used this formula and also use like learning this vector through the model, and they got like really close results. So they're stuck with this formula. So the intuition behind using sine and cosine function is that it should be able to extend sequences longer than what is seen in the training. Sine and cosine has a repetitive nature, right? So it will hopefully be able to extrapolate from the sequence length slightly longer than it is observed in the training. So this is the intuition behind using this formula, and again, it can also be learned from the model. So this is just the code I have kept here. It's just doing the same formula, and if you see the odd positions use cosine function, and the even ones use sine function. So it's just the code here to do that. The next step, I'll move on to the encoder layer. So we have done input embedding, we have added positional information to it, and then we move to this section of the network. which is multi-hit attention layer. So this is the entire encoder layer. So it will have one, as I discussed earlier, every encoder layer have two sublayers, one multi-head attention and another feed-forward neural network. So I'll discuss each in the next slides. Again, if you see this nx here, so this is the number of time you want to have this encoder layer stacked to each other. So in the paper, they have used 6. You can use. Okay, before I go to multi-head attention layer, it is important to understand what self-attention layer is doing. So self-attention is a method that this network use. It actually helps to figure out for a particular word, like, for example, if you think about, I'm sorry, yeah. If you think about this sentence, the animal didn't cross the street because it was too tired. So the word it here, when you are processing this word it, so it is the self-attention mechanism helps to see that it is associated with other words in the sequence. And it also have the power to identify the context of this word with respect to other words in the sequence. So in this sentence, the animal didn't cross the street because it was too wide. Uh, Here it has a different meaning, and the self-attention mechanism have the power to distinguish between this as well. If you see uh, here, the association with the street is strongest, and here association with animal is strongest. So again, I'll discuss this self-attention with an example. So for example, consider this statement, sequence of words. The tree bark is rough. So you do your input embedding, like we represent each word into a vector representation. Then what is done to what we need here is to get some context from of these vectors, right? So what is done here is some reweighing operation is performed, and then we get some vectors which have more context to it. So how this reweighing is done, consider this the first vector. Your you have to do it for every word, but let's consider one for example, then we'll move to generalization. For vector v1, you calculate these scores. So these scores is nothing but a kind of similarity operation, right? We are doing a dot product with each other vectors in the sequence. So this is for the first words only. So you get all these 5 scores. Now, if you do the dot product, you'll get a similarity measure, but it'll be numbers of different scales, right? So to like convert it to a probability distribution, you can, or I mean, you need to normalize this scores. So you can pass through a softmax operation and you get the weights, right? So once we get these weights, remember these weights are only for this vector v1. So you do this operation, this uh, like you multiply each weight with each vector and add them up, you get a y1 vector. So now y1 vector has some context to it, that how other words are associated with the word the. So you can calculate this for each vector. For v1, you get a y1. For v2, you get y2. Again, for when you consider v2, here all this will be v2, and you will have scores like S21, S22, S23, and so on. And you get all these vectors. So these vectors will have some more context to it. So a couple of points to note here is um, we don't like here when I was doing this operation, the order of the sequence has no influence, right? And also the proximity, like V1 were to V5, it also has no influence in this calculation. And these weights are not trained. I'm calculating it right from the vectors I already have. So these are not trained vectors, trained weights. Sorry. So if we can train this or learn these weights from a model, we can learn more pattern or more, we can have a more flexible system. So here comes a new concept, which is key queries and values. So this is just the same operation that we did in the last slide. So you have the sequence of words, you convert it to the embedded vectors, like the vector representation. For example, for if we are looking at this word V2, so we do some dot product operation, we calculate uh, scores. Sorry, so these should be S21, S22. My bad. So this should be the scores for vector 2. Yeah, sorry about that. I think like you're following what I'm trying to say here, right? So again, we normalize this score. We'll get again W2 1, W22, W23, W24, and we get the scores. We do the operations like multiply each weight with vector, and we get like adding these up, we get a vector with more context to it. So if you note here, like this vi, these vectors are represented thrice in this example. So once here and once here and once here, right? So what we would do here, we would add parameters at these positions. So if you think in the context of database retrieval, we can say that we have a query for this second vector. We want a bit of context for this vector. So this becomes my query. And we can assume the vectors in this position are the keys. And we then combine these two with a dot product. And we want to get back to these vectors, which we can refer to as values. So this is not exactly same concept as used in database retrieval, but we just use these terms from there. So thus we can introduce this key, query, and value parameter. So how do we do that? So we know that for any vector, we can have this representation, like if a vector of length k, if we multiply it with a matrix with a square matrix with k cross k dimension, we'll get another vector of k, length k. So we can add these matrices, and these parameter can be learned from the model. Here we add the key matrices, this will be our query, and finally, this will be our value matrices. And these matrices are the weight matrices that we will be learning from the model. So in short, in nutshell, the self-attention mechanism can be described as in this slide. So the vectors are passed through this three linear layer, like one key, queries, values. So keys and queries are multiplied to get this, you get the score, you normalize the score, you get weights, and you multiply this with the value, you get a vector with more context added to it. So in In transformer, we use this self-attention concept in the first layer, which is known as multi-headed attention layer. I'll go to the multi-headed section a bit later, but this is how it is done uh, for self-attention layer. So you have two, for example, you have two words, right, in a sequence. So you did your embedding, and you have now this matrices like query, key, and value. So you get three vectors, queries, keys, and values by multiplying x1 with query matrix, you get q1. Multiplying x2 with query matrix, you get q2. So similarly, multiplying x1 with key matrix, you get q1, k2, v1, v2, and so on. So if you see in this, this queries, keys, and values have a smaller dimension than the input embedded vector. So this is not necessary, but in paper it was done on purpose. I'll say exactly why it is done in a later slide, but it can be like you can use a square matrix here, and you can have these vectors of similar dimension as well. But in paper it was done this way. The operations done here is exactly similar to what I discussed earlier as in the attention mechanism section. So you have this queries, keys, value vector. You calculate the score by multiplying like dot product of query and key vectors. You get a score. Here, one additional step is done. It is divided by the dimension of the key vector, sorry, square root of the dimension of the key vector. This is done to help to get more stable gradient. So you have this number. So you have to make sure that this operation is done for every word. The operation shown here is only for the first word. So you get score for, like, you get score of thinking with each word in the sentence or sequence. So the score for with itself is say 112. The score of thinking with machines is 96. So that's how it goes. So you, after you divide it with the dimension, the square root of dimension, you get this number, and then you pass through a softmax function. So this will help you give a probability distribution. And also, it will amplify the value which is more similar, and also with if the similarity is small, it will uh, reduce it further by multiplying with very small numbers. So once you have the softmax function, that is your probability distribution is here, then you multiply it with value and you get V1 and V2 with some context to it. And then you add all these vectors to get your final vector corresponding to the first word. So you do this operation for every word in the sequence. Yeah, I discussed this slide. Yeah, you need to repeat this for each word. So again, this is the code used for this layer. Whatever like discussed in previous slides is done here in this code. I just kept it for reference. Okay. Next, we move to multi-headed attention. So this is basically what is happening in the first sublayer of the encoder. So multi-headed, like we have discussed self-attention. So when you do like self-attention once, what you're getting at is one perspective. So what multi-headed attention will do, it will get multiple perspective. You can say it will multitask. So in the paper, they have used 8 heads. I'll let you know like what do I mean by heads. Um, the self-attention calculation is repeated 8 different times, with 8 different set of wet matrices. And finally, you get 8 different output matrices. So whatever we were doing in the earlier slides, like the self-attention layer, we're doing it for 8 times. And the reason behind is that you get more perspective for a single word in the sequence. Um, So when you do the operation multiple times, you'll get multiple output matrices as well, right? So, but the output of this layer will go to a feed forward linear layer, so which will expect only one output metrics. So for that, what it is done is like all the outputs from the multiple self-attention heads are concatenated and passed through a dense layer. So you have the similar dimension as your input. Let me explain this a little more. So if you recall the self-attention slide, it's exactly the same, right? But what is the difference is, instead of one key matrix, I'm using H key matrices. Instead of one query, I'm using H query matrices. So how it will help? It will help to see different perspective. It will help the model to understand different perspective of a particular word. So if you see, we have this H uh, heads. It, it, that's what it called, like multi heads. So H keys, H queries, H values, and once you do the similar operation, again you will get the scores, but you will get H score matrices. Then again you do normalizing, you get weight matrices, H weight matrices. It should be one, and finally you get output H vectors with context, right? So to get back to the similar dimension, all the outputs will be concatenated and then passed through a dense layer. Uh, so you get the final output as similar dimension. This is your input. So in the paper, they have used 8 parallel heads. For each of this, I mean, what they did is, while they did the input embedding, they converted each word to a 512 dimension vectors. So they did 8 parallel heads, and as I was saying earlier, they have used a reduced size of queries, keys, and value vector. So they used a dimension of 64, so that when running this 8 multi-head attention layer in parallel, the computation cost remain exactly similar to that of if you run a single head attention with full dimensions. So that's why this they have reduced the size of queries, keys, and value vector with 64 dimension. So as I was saying, the purpose of multi-head attention was to get more perspective to it, to any vector in hand. So it performs different tasks. So this is an example. Here, only 2 heads shown. So if you see that, again, the same sequence, I guess, yeah, the same sequence. So we are concentrating on the word it. So one head is focusing on this part of the sentence and seeing the association between these words. And another head doing, like, parallelly doing operation, and other perspective, whether it is referred to animal, how it is associated with other words in the sentence. So this is only two heads. If you like add in all the heads here, it's pretty difficult to visualize, but for visualization purpose, I think the two makes justice. Again, this is the code for the multi-head attention layer. Um, I've used the self-attention function that is already shown in previous slides. So again, this is reference for the code. And next we move to a layer normalization and residual connection. So if you see this, the encoder layer, every sublayer is followed by a layer normalization and a residual connection. This residual connection is important because it ensures that essential information like positional encoding, etc., is not lost in the way. So if you if you see that this embedding sublayer is only present at the bottom of the stack, it is not present uh, in here, or if you have multiple encoder stack, it is not present in between those. So this residual connection ensures that every layer uh, has a stable input to it. So the output of each sublayer thus forms this layer normalization, crystal connection, and the output of the multi-head attention. And finally, to the encoder layer, the output of the multi-headed attention layer is then passed through a point-wise feed-forward network. Uh, this is a simple, fully connected layer with ReLU activation function used. The input and the output of this layer is same, but there's an inner layer with very high dimensions. So they have used 2048 dimension for one of the inner layer. Again, this is the code reference for the feed-forward neural network. And this is the code where you have all the encoder sublayers added, like the multi-headed attention, point-wise feed-forward network, layer normalization, and how these are used in the model. Again, this is a reference to the code where you add all the required functions for the encoder, embedding, positional encoding, encoder layers, and followed by a dropout layer. Next, we move to this section of the architecture, which is the decoder layer. Now, we have already discussed most of the concept in the network, so there are only few additional concepts to add in this decoder layer, because the two sublayer, like in the decoder layer, you see there are three sublayers. In addition to the two sublayers that we have seen in the encoder layer, the decoder has one third sublayer which performs multi-headed attention over the output of the encoder stack. It's also known as encoder-decoder attention layer. So I'll discuss that in this slide. So before we go detail on this layer, I'll just explain what the decoder does. So in the decoder, the first word is always generated as a special token indicating the start of sequence. So it's called as SOS, which is then converted to an embedding vector in the output embedding layer, then pass through position encoding and pass through all the layers here. And the next word is generated. I'll discuss all these steps in detail next slide. I'm just giving an overview of what it does. So once it generates a word, the next step, the decoder will use the actual output of the current word in the target sequence. So, for example, the sequence, this target sequence is um, like as we let's consider the same example what I had. Yeah, the tree bark is rough, right? So, say, for example, the first, sorry, the first word the decoder predict is I, whereas in the target sequence, the first word is the. So it is not doing the job correctly. But irrespective of that, while it goes to predict the second word, it the actual word, that is the, is provided to the input of this decoder layer. So this is also known as teacher forcing, which actually passes the true output of the next time step, regardless of what the model predicts at the current time step. So it helps to the model to predict a better, do a better prediction for the next word. So this process continues until the entire sequence is completed and it generates a special token, which is end of sequence token, EOS. So I'll go into the sub layers in detail now. So we have already discussed what multi-head attention layer does, but here in the first sub layer, it says masked multi-head attention. So we need to keep in mind during the training phase, the model gets both input and target sequence, right? So it's important that we mask the future words so that the model doesn't, like while predicting, it doesn't see the word it is predicting. So that's why after the positional encoding, the vector is passed through a mask multi-headed attention layer. So the operation is exactly same that we discussed earlier in the multi-head attention layer for encoder, but it is in the decoder phase, we need to mask it for like to predict the second word. You can only see the first first word, and also like to predict the third word, you can only see first, and second word, right? So that's why masking operation is done here. So basically, set them to minus infinity, so that that is not learned by the model. The output of this layer uh, is then passed through another multi-head attention layer. So the purpose or the objective of this layer is um, to for the decoder to understand uh, which word from the encoder output should the decoder focus. So what happens here is the output of this first layer act as a query, and the output from the encoder layer will act as keys and values. So it is like it's like saying that for the word in hand, the word we are working on. So I have this query, which word in the encoder input sequence should I focus on to predict my next output better. So that is what is done in this attention layer. The operation is same. So we know that for multi-head attention, we need three inputs: queries, keys, and value matrix. So we take the query vector from the output of masked multi-headed attention, and we take the key and values from the encoder output. So again, the intuition is to draw information from the encoder layer, that is, which word from the encoder output should the decoder focus with a query from the mask multi-headed attention layer. Then the rest is exactly similar to what we did in encoder layer. So the output then passed through feed-forward neural network, and we need to keep in mind that every sublayer, like we discussed in encoder, every sublayer is followed by a layer normalization and residual connection. Again, this is the compilation of decoder sublayers. So if you see here, for the second attention layer, we are using the out for keys and values, we are using the encoder output, and for the queries, we are using the output from the last attention layer in the decoder. Finally, we have a final layer and softmax function. So the output from the decoder sublayer is again a vector, right? So we want to like predict a word. So the output of decoder layer is passed through a linear layer in the softmax function, and we'll see that a little more in detail. So what happens here? So this linear layer, what it does, it projects the vector to a very a huge logit vector, which is basically the size of your vocabulary. So you have a logit, uh, you have a number for every word, and you then pass it through a probability distribution. So a softmax function, sorry, which gives you the probabilities. So you select the word with the highest probability. So this is what is done in this step. Again, the decoder code is compiled here. So you have the decoder embedding, positional encoding, you have the decoder layer, and followed by a dropout layer. So this is again the code reference compiling encoder, decoder, and the final layer. Yeah, so that's the entire network. And I will have to add uh, the code reference for the training the transformer, and also how do we evaluate that. So I'm yet to add that. Also, I'll add references in each slide. But these are some good reads and some references I've used for creating this presentation. So highly recommended read. So these are very useful informations.
Thank you, Shwati. That was very detailed, very well presentation. So we quickly check from people if anybody has any question on particular thing.
Sure. Yeah.
I have a lot of questions, but I think I'm just going to go through the presentation first and then ask you next time.
Yeah, sure. I have like gone through a lot of things here.
Yeah.
Yeah.
Okay.
Feel free to reach out.